So thank you very much for inviting me to speak at this conference. It's indeed a pleasure to be here. So what I'm going to talk about is joint work with Yuri Berest, Xiaojun Chen and Farko Deshmetov. So I shall begin with a brief introduction. So throughout, by the way, please let me know if I write too small. Okay. So I shall always work over a field K of characteristic 0. Okay. So let A be a commutative algebra over K. So it is very well known what a Poisson structure on A means, right? So a Poisson structure on A, just to recall, is a Lie bracket on A, right? With the additional condition that if I take a fixed element A in A, then bracket to A is a derivation from A to itself, right? So more explicitly, this is just A bracket BC is A bracket B times C plus B times A bracket C for all A, B, C in A. Okay. So one could ask the question, what constitutes a good notion of Poisson structure on non-commutative algebra? Right, and this question has become quite interesting, especially as non-commutative geometry as a field has developed further and further. So to begin with, one could choose to just impose the traditional definition of a Poisson structure and say that a non-commutative Poisson algebra is just an algebra with a Lie bracket having exactly this property that I wrote down. But it turns out that this notion of a non-commutative Poisson structure is extremely restrictive. So there is this result due to Farkas and Letzter dating back to 1998 saying that the commutator bracket is the only Poisson structure on a non-commutative domain up to scalars within quotes. So if A is an NC domain, right, the commutator bracket is the only Poisson bracket on A up to scalars. So I say up to scalars within quotes because scalars means more than just the base field, right? For example, it means things living in a certain extension of the center of A. Okay, but nevertheless, this result should be viewed as one motivation for looking towards notions of non-commutative Poisson structure that are much less restrictive than the obvious one, right? And which nevertheless coincide with the definition of a traditional Poisson structure when applied to a commutative algebra. So motivated by developments in non-commutative geometry over the past, let's say, 12-13 years or so, Crowley-Bovey in 2011 proposed a notion of non-commutative Poisson structure. So he defined what I shall call NC for non-commutative Poisson structures. So his term for this was H0 Poisson structure. Okay. So I shall go into the details of this definition later in this talk, but for now let me just say that a non-commutative Poisson structure on a K algebra A, which might very well be non-commutative, this is a Lie bracket on the quotient space of A by the subspace generated by all commutators. Right? And let me just remind the audience that this is just isomorphic to the zeroth cyclic homology of A, and this Lie bracket has to satisfy some extra condition, which is analogous to the derivation condition here for a traditional Poisson structure. Okay. So of course, when A is commutative, then this definition really coincides with the definition of a traditional Poisson structure. Right. What is also true is that this notion of a non-commutative Poisson structure turns out to have very nice functorial properties that we shall see. In fact, in a more general setting than the setting of honest algebras. Right. But one very interesting property of such a structure, which is the following. So a non-commutative Poisson structure on A this induces Poisson structures on the moduli spaces of isomorphism classes of finite dimensional representations of A. Okay, so this is the moduli space of isomorphism classes of n-dimensional representations of A, and it's an affine scheme. From a certain viewpoint in non-commutative geometry, this is indeed to be viewed as a justification for viewing whatever structure one has on a non-commutative algebra of this kind as a non-commutative Poisson structure, because it was a heuristic principle of Maxim Kontsevich from the late 90s that algebraic structure on a non-commutative algebra A ought to be viewed as the non-commutative analog of a traditional algebraic geometric structure if it indeed induced the traditional algebraic geometric structure on all such moduli spaces in a systematic way. Okay. So what I mean by induce I shall make clear as the talk progresses. Right? So the very fact that Crawley-Bovey called his structures H-naught Poisson structures suggests that there should be a higher homological extension of this notion. Right? And this is indeed what I shall hope to do in this talk. So we shall speak about derived non-commutative Poisson structures. So let me just say that a derived non-commutative Poisson structure on A, this gives rise to a Lie bracket in the graded sense. So let me say graded on the whole cyclic homology of A, whose restriction to the zeroth cyclic homology is a bracket coming from a traditional non-commutative Poisson structure. Right? And just as a non-commutative Poisson structure induces Poisson structures on these moduli spaces of isomorphism classes of representations, a derived non-commutative Poisson structure induces a graded Poisson structure on the derived analogues of these moduli spaces. Okay, so this picture, this Kontsevich principle extends to a very homological or derived setting very nicely. Right, so since the relation between non-commutative Poisson structures and Poisson structures on moduli spaces of representation somehow is at the heart of what we want to study, I need to take a digression and briefly describe representation schemes. And since I am anyway going to do something derived, it makes sense for me to work with the differential graded setting right away. Okay, so let me briefly recall that a differential graded algebra R is a chain complex equipped with a graded K algebra structure whose differential is of course a degree -1 derivation with respect to the product. So explicitly DAB, you want the differential to satisfy a graded form of the Leibniz rule. So this is DAB plus a sign -1 to the degree A, ADB for all AB in R. And when I say for all AB in something graded, I mean for all AB homogeneous automatically. Okay, so R is commutative if it's commutative in the graded sense. -1 chain complex, yes, by convention. Yes. Okay, so R is commutative if it's commutative in the graded sense. So you want AB to be to coincide with BA up to a sign fixed by the Cauchy sign rule. Okay, so notation, I shall use the symbol DGAK and CDGAK for the categories of DJ algebras and commutative DJ algebras respectively. Okay. All right. Okay, so given any fixed DJ algebra, right, one can construct a functor from the category of commutative DJ algebras to the category of sets. Okay, taking each commutative DJB to the set of all DJ homomorphisms from R to the DG algebra of n by n matrices with entries in B. Right? So this has differential induced by the differential on B. Okay. Okay, and the question one, so when B is just a base field, this is just a set of all n-dimensional representations of R, so to say. Okay, so the question is this functor here representable? Okay, and the answer is indeed yes. Okay. So let me summarize this answer in the following proposition. So though the language used is a little category theoretical, it says that not only is this functor representable, but the representing object has a nice functorial construction. Okay, so the functor, taking every commutative DG algebra to the generally non-commutative DG algebra of n by n matrices with entries in the given CDGA. So B to M and B. This actually has a left adjoint which I shall denote by the symbol star A from the category of all DGS to the category of commutative DGS. So this left adjoint actually has an explicit construction, but for want of time I wouldn't want to go into it in this talk. Right? So let me just say in particular, for all R in DGA K and B in C DGA K, one has this adjunction written down explicitly. So home in DGA K from R to the DG algebra of n by n matrices in B, this gets naturally identified with home in the category of commutative DGS from Rn to B. Okay. So, right. So let me just say that spec Rn or Rn should be viewed as the DG algebra of functions on the affine DG scheme parameterizing n-dimensional representations of R. So if R is an honest algebra and it's sitting just in degree 0, right, Rn is an honest commutative algebra, and this is indeed the ring of functions on the representation variety. Okay, so this, let me just call it rep nr. Okay, so in general this is a DG scheme, affine DG scheme. Okay. So there are some nice little consequences of this standard adjunction that follow one after the other. So for one thing, I do have a unit of this adjunction, which means that if I take B to be Rn, the identity here has got to correspond to a certain DG algebra homomorphism here, which is canonical. So you have a canonical DG homomorphism, which I'll denote by pi n, from R to the DG algebra of n by n matrices with entries in Rn. Right? So the second thing we see from this picture about representability is that the group, general linear group GLN K, this acts on Rn by DG algebra automorphisms. Right? So if you want to take an invertible matrix, right, the corresponding endomorphism of Rn, this corresponds under the standard adjunction to post-composing the canonical homomorphism with conjugation by G. Okay. So this means that I could look at the subfunctor of the original sub-functor from DGAK to CDGAK, taking R to the DG subalgebra of those elements in Rn that are fixed under the GLNK action. Right? So this latter DG algebra should be viewed as the DG algebra of functions on the DG scheme parameterizing isomorphism classes of n-dimensional representations of R. So spec RNGL, which is indeed a DG scheme, should be viewed as rep nr mod GLNK. Okay. And finally, one has a trace construction, which is very natural. So I can take the canonical homomorphism from R to the n by n matrices in Rn and then I can post-compose it with just the usual matrix trace. So this is no longer a homomorphism of DG algebras, but it's a map of complexes of k vector spaces, right? And since I'm taking a trace, this composite map vanishes on all graded commutators. So this induces a map of complexes from the quotient complex of R by the subcomplex generated by all graded commutators to Rn, but in fact one can check it lands in the GLN invariant part, right? And this I shall denote by the symbol trace n. Okay. Now note that I've got a map of complexes from a complex to a commutative DG algebra, right? And therefore I have a map of commutative DG algebras from the graded symmetric algebra of this complex to the same commutative DG algebra that I have here. Okay, so this in turn gives rise to, a map which I call sim trace n. So there is some abuse of notation involved here, but this is from sim R mod RR, sim standing for graded symmetric algebra, which means symmetric algebra of the even part tensored with the exterior algebra of the odd part, to R and GL. So this is a morphism in the category of commutative DG algebras. Okay, so this is the basic setup we have. So this last map that I wrote down here, this is actually a very familiar gadget in the case when R is just an honest algebra sitting in degree 0. Right? In the case when R is an honest algebra sitting in degree 0, it is a theorem more than 3 decades old of Claudio Procesi saying that this map is surjective. Right? In other words, traces generate the GLN invariant part of the ring of functions on the representation variety. Okay. So we do have with the Uri Berest an extension of this result to the differential graded setting, which is not immediate from the ungraded version. So let me just write this for the record. So Procesi in the non-graded setting and Uri Berest in the DG setting. Sim trace n is degree-wise surjective. Okay. Now I have all the ingredients I need in order to be able to define and make use of the definition of a non-commutative Poisson structure. So let me remark that the definition that I'm going to write down here is a straightforward extension of Crowley-Bovey's definition to the DG setting. Okay. So the way it works is that a non-commutative Poisson structure on a DGAR is a DG Lie algebra structure on the complex R mod graded commutators. Okay, and then this DG, which we'll denote by just the kind of symbol we use for a Poisson bracket. Okay, and the extra condition is that for each A homogeneous in R, right, a bracket with the image of A in this quotient complex, this is a graded endomorphism of R mod RR of degree equal to the degree of A, and we ask that this be induced by a derivation dA from R to R of degree equal to the degree of A. Okay. So let me first remark that when R is a commutative differential graded algebra, this is just a way of rephrasing the definition of a usual Poisson, DG Poisson structure. Nothing more, nothing less. Okay. Then the second thing I would want to remark is that if R is a non-commutative Poisson algebra, then this complex R mod RR becomes a DG Lie algebra, which means that its graded symmetric algebra acquires a DG Poisson structure. Okay, so let's just point this out as a remark. So R non-commutative Poisson DG algebra implies that sim R mod RR is a DG Poisson algebra. Okay. So for a detailed proof of this statement, one can see some of the earlier papers of Travis Schedler, for instance. Okay, but I think this is a standard fact. Fine. So the following result, right? So this really, in the non-DG setting, it's Crowley-Bovis, and in the DG setting, we have with Yuri Beres, Shaojian and Farco-Deshmet our different, less computational proof, and it is that there exists a unique DG Poisson structure. Structure on RNGL making sim trace n a DG Poisson homomorphism. Okay, this is for all R non-commutative Poisson DG algebra. So there is really, let me remark, because of theorem 1, there is really no choice on what this DG Poisson structure here ought to be. Right? The difficulty is in proving this is well defined. All right. So let me also remark that one has a good notion of the category of non-commutative Poisson DG algebras. Right. So a morphism of non-commutative Poisson DGS is a morphism of DG algebras that preserves the non-commutative Poisson structure. Right. So the next thing I want to discuss is a stronger version of theorem 2. So theorem 2 is part of a bigger result which describes all the nice functorial properties of this notion. Right? But in order to do this, I need to introduce some more gadgets. So let me begin by recalling that a number of the categories we are playing with, namely the category of KDG algebras, the category of commutative KDG algebras, and the category of complexes of K vector spaces. These are all model categories in Quillen's sense of the term. Okay. So it means that these categories have these distinguished classes of morphisms, namely cofibrations, fibrations, and weak equivalences that satisfy some nice axioms among themselves. Right? And what is good about a model category is that one has a good setting to do homotopy theory. In other words, every model category has a homotopy category obtained by inverting the class of weak equivalences. Right? So as far as this talk goes, one can treat this by and large as a black box. Let me just state that the weak equivalences in each one of these model categories is the class of quasi-isomorphisms in that category. Okay? And in particular, the homotopy category of the category of complexes of K vector spaces is just the derived category of the category of complexes of K vector spaces. Okay. So the first question, which is open, is whether the category of non-commutative Poisson DG algebras is a model category, right? So is NC pos K a model category, right? So even though we do not know the answer to this question, it turns out that one can define a reasonable homotopy category of this category. Right, though the construction is somewhat ad hoc. So let omega be the Dirham algebra of the affine line. So this is a commutative DG algebra with generators t and dt in degree 0 and -1, with the derivative of t being dt. So there are evaluation DG homomorphisms for every scalar value of t, which I'll call EVA for t, sending t to a and dt to 0. And these are DG algebra homomorphisms. Right? So also note that if S is a non-commutative Poisson DG algebra, then S tends omega acquires a non-commutative Poisson structure simply by extension of scalars. Right? And therefore one can define a notion of homotopy saying that two morphisms F and G from R to S in this category of non-commutative Poisson DGS are homotopic if there exists a H from R to S tends to omega, with S tends to omega having this extended Poisson, non-commutative Poisson structure, right, such that H0 is F and H1 is G. So H of any scalar simply means post-composing H with the identity on S tensor with the corresponding evaluation map. Okay. So with this I am in a position to set up a homotopy category of non-commutative Poisson structures. So I'll call it host star NC pos. The star to indicate that we still don't know whether this is a homotopy category equivalent sense of the term, right? So the objects are simply objects in NC pos that are cofibrant in DGAK. Okay. So for those who might be uncomfortable with the term cofibrant, let me say that heuristically cofibrant means close to being free as a graded algebra. Right? So any algebra whose generators, set of generators is bounded below in degree and which is free as a graded algebra, this is certainly cofibrant. But there are more such. Okay? And morphisms are homotopy classes of morphisms in NC pos. Homotopy being defined in the sense I just mentioned. So I'll just write in a shorthand mod NC pos K mod homotopy. Okay. And the way this is constructed, it turns out that the forgetful functor from non-commutative Poisson to the category of DG algebras extends to a forgetful functor from this rather ad hoc homotopy category to the homotopy category of DG algebras. Okay. Alright. So the other thing I want to recall is a result due to Yuri Berest, George Kachaturian and I, right, which really amounts to saying that we can define some sort of derived representation schemes. So it says that the functor sub NGL from the category DGAK to CDGAK that I just described somewhere, I think it was there, right? So it has a total left derived functor. So I'll just write left derived for short. Okay, which I'll call L sub NGL from the homotopy category of DG algebras to the homotopy category of commutative DG algebras. Okay, and like any left derived functor, the way this is evaluated is by by taking the class of DG algebra A to the class of the original functor applied to any cofibrant resolution of A. Okay, so for all R. So cofibrant resolution simply means that you want R to be cofibrant, meaning close to free as a DG algebra, and you want it to come together with a quasi-isomorphism to A. Okay? Alright. So I'm now in a position to state the stronger form of theorem 2, which is, so theorem 4, this is due to Berest, Chen, Neshmatov and I. Right, so we have two commutative diagrams of functors. The first one at the level of usual categories and not homotopy categories. So we have from non-commutative Poisson, we have this sub NGL functor to the category of DG Poisson algebras, commutative DG Poisson algebras. So at the level of objects, this is what it does is described in theorem 2. Right? But this is actually functorial. So there is some more to prove. There is a forgetful functor down to DGAK, and then you have still the sub NGL functor going to CDGAK, and you have a forgetful functor here as well. Okay, so this is not so surprising, but even better, is that this kind of picture seems to descend to the level of homotopy categories, right? So you have this homotopy category we constructed, Ho star NC pos K, right? You have from here to the homotopy category in Quillen's sense of the category of DG Poisson algebras, you have a functor which I'll call L star sub NGL. So which means this is a functor which at the level of homotopy DG algebras is the derived sub NGL functor. Okay, and then you do have a type kind of forgetful functor from here to DGAK, and you have the derived sub n functor from here to the homotopy category of commutative DGS, and you have forgetful functors here as well. So this kind of summarizes the nice functorial property of this notion, as well as the fact that these non-commutative Poisson structures induce nice DG Poisson structures on these moduli spaces or moduli DG schemes of isomorphism classes of representations. Okay. Alright, so the kind of situation that I'll be interested in for the remainder of this talk is the situation when R is a free resolution or a cofibrant resolution of honest algebra A. So you want A to belong to just the category of K algebras, viewed as a DG algebra sitting in degree 0. Right? So in this case, so I can make two definitions. So firstly, the derived moduli space of isomorphism classes of n-dimensional representations of A. So this should be simply the derived sub n functor applied to A, sub NGL functor applied to A, viewed as an object not in the homotopy category of CDJK but its opposite category. Right? So derived scheme is just an object in the opposite category of homotopy commutative DG algebras. And then one can also define the representation homology of A, H, A, N, G, L. This is of course just homology applied to this derived sub NGL functor of A. So this is a graded commutative algebra, but I could also view this as a graded vector space. Okay, so let me remark that just a zeroth such homology, this is exactly the ring of functions on the usual moduli space parametrizing n-dimensional isomorphism classes of n-dimensional representations of it. Okay. And then one could define a derived non-commutative Poisson structure on A. So I'm going to say that a derived non-commutative Poisson structure on A is simply a non-commutative Poisson structure on some cofibrant resolution of A. Right? So this definition kind of leads to some open questions which I'll come to later. So a derived NC pos structure on A is a non-commutative Poisson structure on some cofibrant resolution R of A. Okay, so A still is an honest algebra, but R of course is in general DG, right? Unless A is formally smooth or something like this. Okay. So I'd like to kind of discuss what kinds of structures a derived non-commutative Poisson structure gives rise to. So before I do this, I need to recall a result of Feigin and Siegel dating back to 1985. Though it was not stated in their paper in exactly this language, but the result means exactly this. So one has a functor which I'll call C for cyclic, from the category of KDG algebras to the category of complexes of K vector spaces, taking R to the quotient of R by the subcomplex generated by all commutators. Right? It turns out that this functor has a total left derived functor. So it has a left derived functor LC from ODGAK to the homotopy category of complexes of k vector spaces, which is indeed the same thing as the derived category of complexes of k vector spaces, taking the isomorphism class of any DGA to really the class of R mod RR for all R cofibrant resolution of A. Okay. Okay, but the second part, and this is a little more interesting, is that if I apply this derived C functor to a ordinary honest algebra, so for all an honest algebra, right, A can be viewed as a DG algebra in degree 0, and so I can apply the derived cyclic functor to A, and then this being an object in the derived category of complexes of k vector spaces, I can take its homology, right? So it turns out that the homology is isomorphic just to the cyclic homology of A. In fact, this was one of the definitions of cyclic homology doing the rounds in the 80s, right? Though this is not so computation friendly, and therefore it got brushed under the carpet. Okay. All right. So this brings me to a situation where I can summarize the kinds of information one can extract out of a derived non-commutative Poisson structure. So let me kind of draw a diagram. Okay. So suppose I have a derived NC Poisson structure on A, which is a K algebra. So remember, this is an MC Poisson structure on some cofibrant resolution of A. So if I look at what it does on zeroth homology, I first of all extract a non-commutative Poisson structure on A in the usual sense, right? If I just look at what it does to zeroth homology. Right. So the second thing is that by definition, such a structure gives a DG Lie algebra structure on R mod commutators. Right. But by theorem phi, R mod commutators is exactly a complex computing the cyclic homology of A. Right. And therefore one gets a graded Lie algebra structure. The structure on the whole cyclic homology of A, which of course when restricted to zero cyclic homology is the original NC Poisson structure, right? And by theorem 2, right, such a gadget induces a DG Poisson structure on RNGL, right? But the homology of RNGL is exactly the representation homology of A, right? So this induces a graded Poisson structure on the representation homology of A. Okay. Moreover, with an extra property. So remember, right at the beginning we had this trace construction, trace n from R mod RR to RNGL. So when I take homology after applying it to this particular resolution of A, then one gets a map of graded vector spaces trace n from the cyclic homology of A to the representation homology of A, right? And this map is a Lie algebra, a graded Lie homomorphism. Okay. So you get quite a bit here from a derived Poisson structure. So before I go to discuss examples of derived Poisson structures, let me raise two questions which come about because for all that I discussed here, the definition of homotopy category of non-commutative Poisson algebras is somewhat ad hoc. Okay. So the first question is this, and it's both of these are open, of course. Question 1. So given a non-commutative Poisson structure on a on honest algebra A, does it extend to a derived Poisson structure, or are there obstructions to a derived Poisson structure, or are there obstructions, and if there are obstructions, what are they? Okay, and question 2 is if the answer to question 1 is yes, is such an extension unique? Okay, and is such an extension unique? And unique means unique up to isomorphism in this homotopy category that we have. Okay, unique up to isomorphism in Ho star in C cos K. Alright. Okay. So in the final part of this talk, I'd like to kind of discuss some, at least a way of constructing examples of such structures. So this will demonstrate that these structures are not unnatural, they do show up in nature. So okay, so it turns out that coalgebras that are so-called DG coalgebras that are so-called n-cyclic turn out to be a source for construction of non-commutative Poisson structures. So let me recall that DG coalgebra C is n-cyclic, okay, if it has a degree n symmetric bilinear pairing, which I'll call this, with two conditions. So the first is a cyclicity condition. So you want for all V and W and C, V prime paired with W times V double prime, this should be up to a sign coming from the Koszul sign rule, V paired with W double prime times W prime. So here I'm using this Sweedler notation. So I'm denoting the coproduct of V by V prime tensor V double prime and the coproduct of W by W prime tensor W double prime, etc. Okay, and the second, of course, is compatibility with differential. So you want it to be a map of complexes, so you want dVW plus or minus V dW to be always 0. Okay, and this is for all VW homogeneous in C. Okay, so one source of examples of cyclic coalgebras comes from duals of finite dimensional n-cyclic algebras. Okay, so if A is a finite dimensional n-cyclic DVA, right, a dual is a minus n-cyclic DG coalgebra. Clearly. And let me remark, and this is where this Calabi-Yau business comes in, that such DG algebras are examples of DG algebras that are Calabi-Yau in the sense of Kontsevich and Zeubelmann. Okay, such things are Calabi-Yau in the sense of Kontsevich and Zeubelmann. Okay. So before I state theorem as to how one constructs non-commutative Poisson structures from this, I need to recall the notion of a double Poisson bracket. So map of complexes. So this is a definition due to Vandenberg, which I'll denote by a double bracket from R tensor R to R tensor R is a double Poisson bracket if firstly for all A in R you have taking this double bracket with A from R to R tensor R. R tensor R can be given an outer bimodule structure. So you want this to be a derivation of degree equal to the degree of A, of course. And the second thing is one wants an anti-symmetry condition. So the anti-symmetry condition is that for all AB in R, taking the double bracket of A with B, this is minus have plus or minus being sign coming from the Kojoule sign rule of the double bracket with b with a opposite, where this operator opposite from r tensor r to itself simply swaps factors, right? We're again introducing a sign as per the Kojoule sign rule. Okay, so this is just swapping factors, so let me just say swap. And then the third thing, which I shall not write down explicitly, this is the double Jacobi identity. Okay, so if it satisfies all these three properties, such an operator is called a double Poisson structure. Right. I could choose to erase this. Fine. This is okay. So the interesting thing, which is a straightforward extension of one of Vandenberg's lemmas to the DG setting, is that once I have a double Poisson structure, I can always extract a non-commutative Poisson structure from that. So, lemma.
Would you say that's a derivation from R to R tensor R?
Yeah, R tensor. Yeah.
Like bimodule structure.
Outer bimodule structure. So suppose you want B tensor C acting on say X tensor Y, you want it to be BX tensor YC, the outer one. Okay. Again, there are always these signs that come in because I'm working in the DG setting. Okay. So right. So lemma 1 Vandenberg 08. Okay. So if this is a double Poisson bracket on R, then I can form the composite map from R tensor R to R simply by post-composing the double bracket with the product on R. Okay, so the claim is that this induces or this descends to a non-commutative Poisson structure. Okay, and then I'm in a position to state the final theorem that I'll state before passing to the examples. So let C be n cyclic DG coalgebra. Okay, then the point is that cobar C has a degree n plus 2 non-commutative Poisson structure, has a degree n plus 2 NC Poisson structure, which is induced by the degree n plus 2 double bracket by the degree n plus 2 double Poisson bracket. And let me just write its formula. So the V's are elements of a shifted copy of C, and V1 bracket da 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 Vn simply means I'm tensoring these. Okay, so the double bracket of this with W1 Wn, this is just a sum 1 less than or equal to I less than or equal to n, 1 less than or equal to j less than or equal to m of first W, so W1 to Wj minus 1 Vi plus 1 Vn tensored with V1 Vi minus 1 Wj plus 1 yada 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 up to Wn. So actually it turns out that when one looks at the formula for the induced Lie bracket on cobar C mod commutators, this formula bears a lot of resemblance to the formula for Lie brackets in neckless Lie algebras. Okay. So this kind of picture becomes especially interesting if C is n-cyclic and cobar C turns out to resolve an honest algebra. So cobar C by construction, this is free as a DG free as a graded algebra, though not as a DG algebra. Right? So it is cofibrant. So if cobar C is quasi-isomorphic to A, which is an honest algebra, one gets derived n plus 2 non-commutative Poisson structures on A. Okay. So now we should discuss examples. Okay. So the first example is for a very simple coalgebra. Let me just take C to be a three-dimensional coalgebra over the base field with basis elements A, B and S, with these in degrees 1, 1 and 2 with zero differential, no differential whatsoever. And I want the coproduct of S to be A tensor B minus B tensor A. The coproduct of A and the coproduct of B shall vanish for degree reasons. Okay. So then one can check that cobar-C is literally isomorphic to the free graded algebra on three generators X, Y and T with degrees 0, 0 and 1. So these are shifted copies of A, B and S respectively. And the differential that it's equipped with sends T to X, Y minus Yx. Okay.
What in this case is here?
Pardon?
What is the degree of cobar-C?
What is the degree? So I have to shift C, I have to decrease the degrees of the generators, homological degrees of the generators by 1. Okay? And then take the corresponding free algebra. And then there's a differential given determined by this coproduct. And this is what it turns out to be. Okay?
Don't you have to tell us the products of A and T?
Pardon?
Do you not have to tell us the products of A and T?
Yeah, they're 0, I said, for degree reasons. Okay, they're 0. So this is quasi-isomorphic. One can check to simply the algebra of polynomials, commutative polynomials in X and Y. Okay. Now, so the first thing I'd want to say is that C has a unique degree. Unique means unique up to scalar multiplication. Right? Unique degree minus 2 cyclic structure. Okay, so with the cyclic pairing, omega satisfying omega AB is 1. Right, so BA is related to AB, so that's fine. And omega AS and omega BS are going to be 0 for degree reasons. Right, so this in turn is going to give NC Poisson structure on cobar-C without any shift, degree 0. Right, and this in turn is going to give me a derived Poisson structure on KXY. By definition. Right. So this NC Poisson structure arises from theorem 6, and this is literally just by definition. Right. And now remember that from a derived Poisson structure I get a non-commutative Poisson structure on KXY. But the non-commutative Poisson structure on a commutative algebra simply means traditional Poisson structure. Right? So the traditional Poisson structure that I get on KXY is simply the usual one corresponding to the symplectic form dx wedge dy. That's why I recover the standard one. But then I also get a graded Lie structure on the cyclic homology of this algebra of polynomials in 2 variables. Right? And because I'm playing with an augmented algebra, this is augmented over the base field, this graded Lie structure actually ends up descending to the reduced cyclic homology. Okay, where it has a nice geometric meaning. Reduced cyclic. So let me remind you that this guy stays in 2 degrees. So in degree 0 it is just a copy of the original algebra modulo the base field, and in homological degree 1 it's the quotient of the space of 1 forms modulo differentials of 0 forms. Right? So given that this is a bracket of degree 0, I can look at the bracket of the image of 2 functions, and I can also look at the bracket of a function with a 1 form. Right? And each of these has a nice geometric meaning. So let me denote this graded Lie structure by bracket NC, NC standing for non-commutative. Then it turns out so let me take this board as well. Then it turns out that if I take the image of a function and take the non-commutative bracket with image of another function, this is not so surprising. I just take the 2 functions and take the bracket with respect to the standard symplectic form and take its image. Right? And if I want image of a function with the image of a one form, this has a nice meaning. So this turns out to be the following. So I take the Hamiltonian vector field coming from this function because of this symplectic form dx wedge dy, and then I take Lie derivative of that one form with respect to this Hamiltonian vector field, and then I take its image. Right? So this indicates that not only do derived non-commutative Poisson structures exist, sometimes they have some nice geometric meaning. Okay? Let me make one more remark. So, though I shall not write it down, it turns out that C also has a unique degree -3 cyclic structure up to scalar multiplication. Right? And now if we do the same thing, you get a derived -1 Poisson non-commutative Poisson structure on A. Right? So of course you cannot have an honest degree -1 non-commutative Poisson structure on A simply for degree reasons. Right? But you have a derived one, and that is actually non-trivial. So of course the bracket for the -1 Poisson structure between two functions is 0, but the bracket in the -1 Poisson structure between a function and a one form, this is in general not 0, though we haven't yet found a good geometric interpretation for that. Okay, so let me finish with a final example of such a thing coming from topology. Right? So let M be a compact, smooth, oriented N manifold. Okay. Then some years back, Chas and Sullivan in 2004, if I am not mistaken, they showed that the S1 equivariant homology of the loop space of M has a degree 2 minus n Lie bracket. Okay. So that construction was rather topological, right? It was of a topological nature, but this framework can give an algebraic explanation for how such a structure arises. Right? And the way this happens is as follows. So there is the recent work of Lambrechts and Stanley from 2008, which is that there exists a finite dimensional -n cyclic DG coalgebra, which I'll call CM. Okay, so that CM turns out to be actually quasi-isomorphic to the homology of M. Right? Homology meaning you could say dual of the de Rham cohomology, for instance. And the pairing on CM, this induces simply the intersection pairing. Okay. And then it is also a result of Chen, Ashmatov and Gunn. William Gunn, that if you take the cyclic homology of Kobar of this coalgebra, right, this turns out to be actually isomorphic to the S1 equivariant homology of the loop space of M. Right, so again by theorem 6, this -n cyclic structure here induces a 2 minus n non-commutative Poisson structure on this Kobar DG algebra, which in turn gives of course a 2 minus n shifted graded Lie structure on the corresponding cyclic homology. Right, so this is how it arises. So maybe I should stop here. Thank you.